All right, here we go. Chapter 9, problem set number 1. We're going to start with question number 3. Question number 3 says, consider a box that explodes into 2 pieces while moving with a constant velocity along the x-axis. Okay, so let's see what the initial condition may have looked like first, and then we'll get to the final condition. So it's a box that's moving along this surface here at a constant speed. It's apparently pink, so we'll draw it thusly. So this is the box moving before. So what's going to happen is it's going to explode into 2 pieces. Well, an explosion is actually just one force. It's a Newton's third law force pair, ostensibly, that's going to push on each of these. So what that tells us is all the forces are inside the system. And if all the forces are inside the system, total momentum is conserved. So in this case, what we're going to notice is that the total momentum must be a vector that looks like that. And so how are we going to get this over here? Now, these are just velocities, but because each of these has the same mass, which is half the mass of this thing, we can get a good sense of what's going on here. So the problem says, if one piece with mass m1 ends up with a positive velocity v1, then the second piece with m2 could end up with a positive velocity v2, that's A, a negative velocity v2, that's B, or C, zero velocity. Rank those 3 possible results for the second piece according to the corresponding magnitude of the first piece greatest first. Well, what that's saying here is like, if v2, or if this piece over here ends up with speed v2, what has to be true about v1? If this is moving this way, what has to be true about v1? And if this one stopped, what has to be true about v1? Well, consider for a moment that the total momentum has to stay the same. So if v2 has some momentum in this direction already, then v1 doesn't need very much momentum because those two together should add to this one. This one, on the other hand, if v2 ends up with momentum in this direction, then v1 has to have a ton of momentum in this direction. Because this plus this have to equal this. And this one over here, if this one ends up stopped with no momentum, then this one has to have basically the same momentum as this one. So I'm going to go greatest first. I'm going to say B is going to have the greatest V1, and then C, and then A. Let's go on to the next one. This is question 7. Question 7 says, a block slides along a frictionless floor and into a stationary second block with the same mass. So, okay, so let's draw what the initial condition might look like. Okay, so we're going to have a block. It's going to slide along and collide. Slide along and collide with another block. Now, a couple of things could happen here. This could hit and stick together, and they could move off together, or they could bounce off. We don't really know what the masses are. So but some kind of collision is going to happen here. So we only have a couple choices here. Either they hit and stick, that would be an inelastic collision, and the total energy before would be greater than the total energy after because you lose some in the collision, or it could be an elastic collision where the energy is conserved. And so what we're going to try to find out is what's going on with these energies here. So let's look at A. Okay. Let's look at A here. Well, what I notice about A is if I look at the total energy before, it's 1, 2, 3, 4. The total energy before is 5. The total energy after, this is 1, this is 1, 2, 3, 4. So in A, it looks like the total kinetic energy initial is equal to the total kinetic energy final, and we would then term that an elastic collision. Let's look at B over here. All right, so B, I have 0, 1, 2, 3, 4. So the initial kinetic energy is 5. Kinetic energy after is 1 plus 1, 2, 3. So it looks like the kinetic energy initial is actually greater than the kinetic energy final. That's fine with us. We call that an inelastic collision. Okay, what's going on with C here? Now this is weird here for C because if you notice, our initial energy is 5 and 0, but our final energy, this is here -1. All right, so this is C is an impossible situation because it has kinetic energy that's less than 0, and that's not true. You can't have kinetic energy that's less than 0. And what about D here? Well, I'm going to notice here I have initial kinetic energy is 0 and 1, 2, 3. Final kinetic energy is 1 plus 4. That would be 5. So this is also an impossible situation because the kinetic energy initial is somehow less than the kinetic energy final. And that doesn't make any sense because you can't gain energy in a collision. Let's look at question 11. Question 11 says, a block with mass M1 slides along the x-axis on a frictionless floor and then undergoes an elastic collision with a stationary block 2 of mass M2. Okay. So let's diagram that up. Now, in this situation, we don't know the mass of the blocks. So they could have the same mass, or M1 could be bigger, or M2 could be bigger. So this one is M1. So the question is, what happens if M1 is greater than M2? What happens if M1 is less than M2? And what happens if M1 is equal to M2? So, in the first situation it says, all right, in which of the lettered regions on the graph will the plot be continued after the collision if M1 is less than M2? All right, so let's try to figure out if M1 is less than M2. So that's A. M1 is less than M2. Well, the thing we know is if M1 is less than M2, it's going to hit and rebound. So that's something we've seen in class. That's a good understanding that we have. So M1 is going to come back. So M1 rebounds, therefore the position decreases and slower than before. So what region is that? Well, if it rebounds, the position that has decreased, so it's got to be C or D, and slower would be less steep. So I think it's going to be in region C. B says, what happens if M1 is greater than M2? M1 is greater than M2. Well, we know if M1 is greater, it's going to hit and continue, but slower. So M1 continues. So the position increases, but slower. So if it continued along this line, along the line here, 2 would be at the same speed. All right, so it's got to be, position is increasing, so A or B, but A would be steeper, B is less steep, so I think region B. And C says, what happens if M1 is equal to M2? Well, if M1 is equal to M2, we know that it hits and M1 stops and M2 continues on at the same speed. So, since because M1 stops, his position is not going to change, so it's along line 3. All right. Let's move on to problem number 3. A slab with dimensions D1 is 11, D2 is 2.8, D3 is 13. Half the slab consists of aluminum, density 2.7, and half consists of iron, density 7.85. What are the x, y, and z coordinate of the slab's center of mass? Okay. So this one is actually quite challenging because we're going to have to apply all of our pieces of information, but let's write down what we know first. Okay. Let's write down what we know. So first of all, the thing we know is that D1 is equal to 11, D2 is equal to 2.8, and D3 is equal to 13. We know the density of aluminum is equal to 2.70, and the density of iron is equal to 7.85. Okay, those are the things we know. So the way to start this problem is we're going to shrink each of these halves of the slab down to their own individual centers of mass. So for example, this iron center of mass is going to be right in the middle, X, Y, Z in the middle. And this aluminum center of mass is going to be right in the middle of the aluminum center of mass. And so given the coordinate plane that we have here, okay, we want to try to figure out where these individual centers of masses are of the iron half and of the aluminum half. And we can just use symmetry principles to figure that out. So we're going to take our coordinate, like our 0, 0 down here. We're going to take our 0, 0 down there. So where do you think, when we look at this, where's the iron center of mass? Okay. Well, the iron center of mass is going to be, well, this is the x direction, is this way. So I know it's going to be halfway between here and here. That's halfway along D3. So D3 is 13. So the iron center of mass is going to be 6.5 in the x direction. In the y direction, that's this way, well, the iron center of mass is halfway between this edge and this edge. We know that's 11, so it's at 5.5. And then in the z direction, up and down, it's halfway up. So if the total up and down is 2.8, this would be 1.4. So this is the iron center of mass. Where do you think the center of mass of the aluminum is? Well, in the x direction, that's this direction, it's still halfway. So I feel okay about that, so 6.5. But where, if given this is the 0 here, where is the center of mass of aluminum? Well, it's halfway between the middle and this edge here. So if the total is 22 and this is half is 11, so I think it's 11 plus half of 11, which is 11 plus 5.5, is that 16.5? So this is going to be a 16.5, and in the up and down direction, in the z direction, it's still symmetry 1.4. So what I like about this is you can tell that it's only the y direction that's going to matter, because of symmetry, the up and down, the z direction, it's going to be in the middle. In the x direction, it's going to be in the middle, but the y direction is where things are different. So let's talk about how we're going to do that. Well, one thing we need to know is we know that when we talk about finding the center of mass, we need to talk about the mass. And so we need to somehow figure out the mass. Well, one thing we remember from our study is that if you want to calculate the density, you can take the amount of matter in an object and divide by the volume of that object. This will tell you how densely packed it is. So if you want to calculate the mass, you're going to take the rho times the volume. So let's do that for each of these. So if I want to get the total mass of the iron, I'm going to take the density of iron and calculate the volume. Well, let's look at this half of the slab here. What are the densities? It's length times width times height. So I'm going to say that's the length is 11 times 2.8 times 13. Put that in my handy dandy calculator. So I have 7.85 times 11 times 2.8 times 13. Got 3143. Okay, and that would be grams. So the same thing for aluminum. Oh. Its density is 2.7. Eleven times 2.8 times 13 times 2.7, 1081 grams. All right. So now what I'm going to do is I'm going to try to find the center of mass in the y direction. So to do the y center mass, I'm going to take m1 y1 plus m2 y2 all divided by m1 plus m2. And what I like about this is that what we're talking about here is this is the mass of the left slab. This is the mass of the right slab. This is the positions of their individual centers. So by shrinking these things down, okay, you got these centers of mass, and we're going to then shrink shrink them down 2 points. Then we're gonna add them up. Okay, let's do the mass of the iron. That's the first one we did. So the mass was 3143, and its Y position was 5.5, plus the mass of the aluminum was 1081, and its position is 16.5. Divide the whole thing by okay, let me add this up, see what I get. And I got 8.3. So this is the Y center of mass. Now, if I ask myself, does this make some sense here? Well, I'll draw a blank. If I'm looking at this here, I know the center of mass has to lie along this line. We know this right here is 11, and so 8.3 might be right back here. And that makes sense to me that the iron is more massive, so the center of mass should be shifted over there. 8.3 makes sense. So, what are the x, y, and z coordinates? Well, x center of mass is going to be 6.5 because of symmetry. Y center of mass is 8.3, and the z center of mass 1.4. All right. Last one says, what are the x, y, and z coordinates of the center of mass of the uniform plate shown? Length is equal to 5 centimeters. All right, so let's start this one. One thing you'll notice here is that this is the 0, 0 coordinate here. It's right there. Now, what we're going to do is we're going to try to find the center of mass of each of these plates in the center there, in the center there, in the center there, and in the center there. That one's a little off. I can do better. And we're going to shrink each of these down to its point, and then we're going to use these points and their masses, and we're going to use the formula. So a couple things are important about this. Let's label these all. Let's give them labels. Let's call this plate number 1. We'll call this plate number 2. We'll call this plate number 3, and we'll call this plate number 4. Let's figure out where the centers of masses of each of these plates are. So, 1 center of mass. Well, we're going to do it in terms of L. So, if this is 0, 0, and this is 4L, we know it's 2L. I'm going to leave the L's off. So it's 2 over, and how many tall? So that's 3. It's 3 to the top. So it's got to be halfway between 2 and 3. What about 2 center of mass? Well, 2's over here, so it's to the left, so it's -1. And then it's 3 tall, so half of that, so 1.5. 3 center mass, it's got to be over, so -1 and -2. And where's the 4 center mass? It's right 1 and then down 2, down 3. So I have my centers of mass. That's pretty cool. What about the actual masses themselves? Well, it says these are uniform plates, so we're going to assume uniform thickness. So the area is proportional to the mass. So if I look at the area for 1, area for 1 is 1 times 4. Okay, the area for 2 is equal to 2 by 3. It's 4, so 2 by 4. And this one here is 2 by 2. So because area is proportional to mass, we're actually going to use these values as the mass, which I think is really cool. So let's do it up. Let's do the x's first. So we know that the x center of mass should be equal to m1 x1 plus m2 x2 plus, in this case, m3 x3 plus m4 x4, all divided by m1 plus m2 plus m3 plus m4. Okay, well, mass of 1 is 4, times x position is 2, mass of 2 is 6, times x position is -1, plus mass of 3 is 8, times x position is -1, mass of 4 is 2, x position is 1. Divide this all by the masses. 4 plus 6 plus 8 plus 2. Put this in my handy dandy calculator. On top we have 8 plus -6 plus -8 plus 2. I have a typo. 2 times 2 is 4. Let me fix it up here. Sorry about that. Mass times position, mass times position, mass times position, masses. 4 times the position. There we go. Okay, let's put this in our handy dandy calculator. So on the top I have 8 minus 6 minus 8 so I have -2 on top divided by 22. Now, we did this in terms of L. So to get the actual position, I have to multiply by L, which is 5 centimeters. And I end up with a position of -0.45 centimeters. So it's negative. So it's just to the left a little bit. Okay, let's do the Y. Okay, let's plug and chug this one. Mass is 4. Y position is 2.5. Plus mass is 6. Times Y position is 1.5. Plus mass is 8. Times Y position is -2. Mass is 4. Times Y position is -3. And this is divided by 4 plus 6 plus 8 plus 4. Put this in my handy dandy calculator. negative 0.41. Again, we did it in terms of L. I got negative 2.0. So the X and Y positions of the center mass. I got negative 0.45 and negative 2.